Hi, my name's Carron Shankland. I'm a Professor of Computing Science at the University of Stirling. Thank you very much for inviting me to talk at Lovelace today. Okay, first thing I'm going to do is slide me up into the corner. I might move me around a wee bit during the presentation as well. Okay, so I'm going to talk about model making. That's my area of research. And I don't do this on my own, I do it with collaborators, and I'm mentioning down the bottom here for this specific work, Brian, David, Dalila, David and Kevin. So I love modelling. It's really good. It's a way of creating order out of the complexity of the world. And so for me, modelling is a way of writing a computational model of a complex system, usually a biological system. So I've been doing biological systems for a while. And the really nice thing about modelling is you can try out different scenarios, different models, see what happens. You can explore solutions to problems without having to execute them in the world, so you can discover which one is the best solution. We've seen a lot of that this year with COVID, and so you can see at the bottom I've got a couple of models, a computational one and a mathematical one, and a couple of model outputs, which I'm sure you've seen a lot of this year. So you know that there are a lot of different kinds of models around. They produce different kinds of results because they include different sorts of features. Okay, so what is good about modelling and what is bad about modelling? I think, so what I love about modelling is that early part where you're trying to understand the problem. You can talk to the domain experts, in my case the biologists, to really understand what it is that their problem is, and to try and extract the most important details from that problem that you then put into a model. You parameterize that model with observed data, you hope, if you can, if you've got enough observed data, and then you run or you simulate or you analyze that model. Usually at that point, you discover that you didn't have the right parameters. So you go back and you try some other parameters. Or you discover that you made an error in your code. None of us is infallible. You go back and you fix the errors in your code. Or most often of all, you discover that you didn't really understand the problem at all, and you go back and talk to your collaborators a bit more to try and figure out what it was that you really should have captured in the first place. That one, it's about communication. There's not really an awful lot you can do to make that better, but you can use tools to help you do the parameterization at least. And so that's what I'm looking at, so that you can use modelling time to create the model and talk to the domain experts and not spend it parameterizing your model. So how are we going to do that? So what's difficult about the parameters? So partly the parameters are difficult because some of them I can measure. So for example, if I'm thinking about a disease model, I can measure the number of people in the population. I can measure how many people have gone into hospital. But others are quite hard to measure, so we don't actually have a good handle on the precise number that I can put into my model that's going to make it work, that's going to make it match the observed data. So I don't even think about COVID. I don't even know how many people are infected in the population. I'd have to test everybody in the population every day to get a good number for that. It's just not feasible. Similarly, I can't test things like how many contacts a person makes per day, how many infectious contacts a person makes per day, because that will vary depending on your viral load, the susceptibility of the person that you're talking to, how close the contact was, what the air temperature or the breeze was, all sorts of things. So these are all unknown for us. We can put brackets around them, but we don't necessarily know a specific number. And worse than that, there's a lot of variability in the population anyway. So in biological systems, there's a lot of uncertainty about what the parameters are, whether we can measure them, but also there's just a lot of variation. So some people will get a disease for longer, some people will have it for a short time, and that's just natural, right? Normal distribution or whatever. So if we've got a lot of parameters, what does that mean? Let's say we have a certain number of parameters and a certain number of values. Then the total number of parameter sets that I can have is just those two figures multiplied together. If I have 9 parameters and each of those can have 2 values, I have 18 variations. That's very easy to search through all of those variations, try them out and see what happens in the model. If I have parameters that range over 0 to 10 in increments of 0.1, oh, that's more parameters, right? So now I've got 900 variations. I do not want to do that by hand. That'd be crazy. It gets worse because actually in biological systems we're probably looking at more parameters and also bigger increments, smaller increments, more variation in the number of values. So that's nearly 500,000 variations. I can't do that. If you think about the time that it takes to compute this, if the model runs for 1 second, 18 seconds to explore the space, fine. 900 seconds, that's 15 minutes, okay. 450,000 seconds, it's too much. That's 125 hours. I can't do that every time I want to explore the space of the model. Okay, so what do I do? The way we've approached it here, let me just move myself out of the way, is we combined modelling with evolutionary computation. So the idea is you take your basic model and observed data, you feed those into a process which is going to have, for example, a genetic algorithm in it. That will mush around for a while and hopefully produce us a better model. And in this case, what we're interested in is, given a particular model, what parameter settings fit my data. So I can give it the observed data and ranges for the parameters that I don't know, and it will come out with the right version of the parameter settings. Brilliant. Okay, I'm not sure if you know what a genetic algorithm is. It's a search heuristic. So we use it to explore the parameter space that we have. So imagine the parameter space. Here's my picture. I've drawn this as a 2D space because 45 dimensions is quite hard to draw. So imagine that I just choose a set of values across this space, and that's what these yellow dots are in the space. And then I apply a measure because I know what the desired outcome is. I know that I have some target observed data. So I know that when I run my model, if it looks like the observed data, then my parameter settings are good. If it doesn't look like the observed data, my parameter settings are not good. So I can think about that in terms of graphs. So which one of these graphs matches the solid red line best? I choose that solution. So then I just have to throw away the poor ones, keep the good sets of parameters, and maybe add in a bit of mutation so that I explore a bit more of the space. And I just repeat until there's no more improvement. And I can do this because I've got a measure. So I know how good the parameters are. So that means that I can say, every time I run this process, I can take the best solution that I've got so far and say, how good is that solution? And here I'm going to measure best in terms of close to 0, so the closest match. So as I go through the repetitions here on this loop, then my fitness gets closer and closer to 0. And eventually it flattens out and I'm not getting any more improvements. So I know that it's time to stop that process. I've got the best solution that I can. Hurrah! Do I know if this is the best parameter set that I could possibly have? Is it, for example, let me just go back. Is it, for example, this highest peak? Let's say that's going to be the best solution. Is it that highest peak, or is it one of these more local peaks? Okay, so, but of course it's not quite that simple. I'm going to illustrate what we can do to cope with that complexity by looking at a particular case study. So I'm going to look at a model that we did of HPV, the human papillomavirus. It's interesting because we've got quite a lot of information about it, and we can look at a variety of different strategies to deal with HPV, to include different strains of the virus and so on. It's also linked to cancer, and so that gives us other interesting things that we can put in the model. And that's also why it's interesting to look at, because we would like to prevent some of these cases of cancer. So the good news is, for HPV, we have vaccination. In Scotland, which is where we got our data, females between 12 and 13 have been vaccinated since 2008. And we've got a 7-year study, 7 years of data that show a significant reduction in HPV prevalence, which is good, and also a reduction in the numbers of cervical pre-cancer cases. Where can we go next with this? So we made a model. My student Ryan made the model. He was an honours student a couple of years ago, and one of the things I think is really nice, and the reason I wanted to present this today, was because he's an honours student. You could do this, right? Any of you could take this kind of work and potentially turn it into some kind of publication as well. You could work with your supervisor to make a really nice piece of work. So Ryan made a model based on this kind of classic disease model, SEIR we call it, and he added some extra things. So he added vaccination, gender. He added that women have sex with women as well as men having sex with men, and not just heterosexuals. And he added the precancerous stages. It's a nice model. Here is a schematic. I'm not going to give you the code for it, but it's just to give you an idea of what's going on. So you can see down here are the males, and the males are exposed to disease. They might get infected and they become immune over time. We've separated out 2 different sets of strains that we're interested in here. The ones that we're vaccinating against and the ones that we're not vaccinating against. The women are similar. So again, exposed, infected, immune. But what I've got in the middle here are the precancerous stages. These are the ones labelled CIN. And what I want you to particularly notice here is that this is a wee tricky bit of the network, because I can go to CIN1, but I might come out via immune, or I might go into these other cancerous stages. So it's not a straightforward progression the way it is when we go from exposed to infected to immune. Okay, so what do I want to do with this model? There are many things that I don't know. In particular, it's not clear how we progress from one stage of CIN to another, and the rates at which we do that. And also we can go backwards in that loop. Again, it's not clear how that happens either, or the rate at which that happens. So I want to discover these unknown parameters. And then I want to use the parameterized model to explore vaccination and other immunities. Okay, so I run the GA and I get an answer out. I have a bunch of numbers, but I've got no idea what those numbers mean, actually. So are these good numbers? Are these bad numbers? I can't tell. I'm lacking confidence in the solution here. I'd like some context that tells me how good these numbers are in relation to the whole parameter space, but without doing that calculation of the whole parameter space. So for GAs, I have to do it more than once. I have to do it a lot. And then I choose the best of the best solutions. Yeah, so I have more confidence because of the repetition of those calculations. So here is a graph showing what happens. I'm going to zoom in on this, don't worry, I know it's too small to see. But the overall picture is that this shows all of my variables. It shows the top 20 solutions graphed from 100,000 that we tried, and that was out of 7 times 10 to the 16 possible parameter sets. Okay, so that was a lot. It's too many to calculate. So we calculated a sample basically, and we want to know how good is that sample. So for example, when I zoom in here, you can see I've got the fitness and contact and immunity. These are 3 of my variables, well, 2 of my variables plus the overall fitness of the GA graphed against each other. And what you can see is, for example, in my 20 solutions, fitness is not very clearly distributed. It might be a normal distribution, but it looks possibly as if it might be a bit more flat. Contact is a very skewed distribution, so it goes up to the highest number it possibly can. The other thing that I've got here in this graph, which is useful, is that I have scatter plots of one variable against another. So you can see here, for example, fitness against contact, and that shows how fitness varies with the contact rate. And the answer is there's no particular correlation there. There's no relationship between fitness and contact rate. But if I look at immunity and fitness, there's a huge correlation between immunity and fitness. In fact, the number that I get, the correlation value is 0.95. So a perfect correlation would be 1. So this is telling us that fitness goes up when immunity goes up, fitness goes down when the immunity rate goes down, the rate by which we transfer to the immune state. So that can tell us something important about our model, and we can then go back and look more at the model, look more at the analysis, and it's enabled us to hone in more closely on the important features. Once I've got the model parameterized, I can then do things like look at what are the impacts of different vaccination strategies. So here you can see I just vaccinate women, and I still end up with levels of the disease in the future. But if I also vaccinate men, boys, then I can see the levels of the disease drop off. Okay, what happens next? So in this work, there are fortunately many more steps that I could look at. So I could extend the model to have more features, and there's a range of different biological features that I can add in. And I can also extend the framework, because there are some things around the way we've used the GA that we could improve, and the way that we match the simulated data to the observed data. There are lots of different ways that we can try to do that might give us different results. So I hope that you've learned something about modelling and genetic algorithms here, and I hope that you maybe think about doing modelling in your own honours projects or in your own degree.